Let me talk to you about parallelism. In your post titled Reasoning About Async IO Semaphore, you talk about a fast food restaurant in Silicon Valley that has only one table. Is this a real thing? I just wanted to ask you about that. Is that just like a metaphor you're using, or is that an actual restaurant in Silicon Valley?
It was a metaphor, of course.
Okay. I can imagine such a restaurant. So for people who didn't read the thing, you should, but it was idea of a restaurant where there's only one table and you show up one at a time and you're prepared. And I actually looked it up, and there's restaurants like this throughout the world. And it just seems like a fascinating idea. You stand in line, you show up, there's one table. They ask you all kinds of questions. They cook just for you. That's fascinating.
It sounds like you'd find places like that in Tokyo. It sounds like a very Japanese thing. Or in the Bay Area, there are pop-up places that probably more or less work like that. I've never eaten at such a place.
The fascinating thing is you propose it's a fast food. This is all for a burger.
It was one of my rare sort of more literary or poetic moments where I thought I'll just open with a crazy example to catch your attention, and the rest is very dry stuff about locks and semaphores and how a semaphore is a generalization of a lock.
Well, it was very poetic and well delivered, and it actually made me wonder if it's real or not, because you don't make that explicit. And it feels like it could be true. And in fact, I wouldn't be surprised if somebody like listens to this and knows exactly a restaurant like this in Silicon Valley. Anyway, can we step back and can you just talk about parallelism, concurrency, threading, asynchronous, all of these different terms? What is it? Sort of at a high philosophical level. The fisherman is back in the boat.
Well, the idea is if the fisherman has two fishing rods, since fishing is mostly a matter of waiting for a fish to nibble. Mm-hmm. Well, it depends on how you do it, actually. But if you had if you're doing the style of fishing where you sort of you throw it out and then you let it sit for a while until maybe you see a nibble, one fisherman can easily run 2 or 3 or 4 fishing rods. And so as long as you can afford the equipment, you can catch 4 times as many fish by small investment in 4 fishing rods. And so since your time, you sort of say you have all Saturday to go fishing, if you can catch 4 times as much fish, you have a much higher productivity.
And that's actually, I think, how deep sea fishing is done. You could just have a rod and you put it in a holster and you can have many rods. Is there an interesting difference between parallelism and concurrency and asynchronous? Is there one a subset of the other to you? Like, how do you think about these terms?
In the computer world, there is a big difference. When people are talking about parallelism, like a parallel computer, that's usually really several complete CPUs that are sort of tied together and share something like memory or an I/O bus. Concurrency can be a much more abstract concept where you have the illusion that things happen simultaneously, but what the computer actually does is it spends a little time running this program for a while, and then it spends some time running that program for a while, and then spending some time for the third program for a while.
So parallelism is the reality, and concurrency is part reality, part illusion.
Yeah, parallelism typically implies that there is multiple copies of the hardware.
You write that implementing synchronization primitives is hard in that blog post, and you talk about locks and semaphores. Why is it hard to implement synchronization primitives?
Because at the conscious level, our brains are not trained to sort of keep track of multiple things at the same time. Like, obviously, you can walk and chew gum at the same time because they're both activities that require only a little bit of your conscious activity. But try balancing your checkbook and watching a murder mystery on TV.
Yeah.
You'll mix up the digits or you'll miss an essential clue in the TV show.
So why does it matter that the programmer, the human, is bad?
Because the programmer is, at least with the current state of the art, is responsible for writing the code correctly. And it's hard enough to keep track of a recipe that you just execute one step at a time. Chop the carrots, then peel the potatoes, mix the icing.
Mhm.
You need your whole brain when you're reading a piece of code. What is going on? Okay, we're loading the number of mermaids in variable A and the number of mermen in variable B, and now we take the average or whatever.
I like how we're
and
just jumping from metaphor to metaphor. I like it.
You have to keep in your head what is in A, what is in B, what is in C. Hopefully you have better names. And that is challenging enough. If you have two different pieces of code that are sort of being executed simultaneously, whether it's using the parallel or the concurrent approach, if like A is the number of fishermen and B is the number of programmers, but in another part of the code, A is the number of mermaids and B is the number of mermen, and somehow that's the same variable. If you do it sequentially, if first you do your merpeople computation and then you do your people in the boat computation, it doesn't matter that the variables are called A and B, and that is literally the same variable because you're done with one use of that variable. But when you mix them together, suddenly the number of merpeople replaces the number of fishermen, and your computation goes dramatically wrong.
And there's all kinds of ordering of operations that could result in the assignment of those variables. And so you have to anticipate all possible orderings.
And you think you're smart and you'll put a lock around it. And in practice, in terms of bugs per 1,000 lines of code, this is an area where everything is worse.
So a lock is a mechanism by which you forbid only one chef can access the oven at a time.
Something like that.
And then semaphores allow you to do what? Multiple ovens?
That's not a bad idea, because if you're baking cakes and you have multiple people all baking cakes, but there's only one oven,
Yeah.
then maybe you can tell that the oven is in use, but maybe it's preheating. And so you have to, maybe you make a sign that says oven in use. And you flip the sign over and it says oven is free when you're done baking your cake.
Mm-hmm.
That's a lock. That's sort of, and what do you do when you have two ovens, or maybe you have 10 ovens? You can put a separate sign on each oven, or maybe you can sort of, someone who comes in wants to see at a glance, and maybe there's an electronic sign that says there are still 5 ovens available.
Mm-hmm.
Or maybe there are already 3 people waiting for an oven, so you can't. If you see an oven that's not in use, it's already reserved for someone else who got in line first. And that's sort of what the restaurant metaphor was trying to explain.
Yeah, and so you're now tasked. You're sitting as a designer of Python with a team of brilliant core developers, and you have to try to figure out to what degree can any of these ideas be integrated and not. So maybe this is a good time to ask, what is async IO, and how has it evolved since Python 3.4?
Wow, yeah. So we had this really old library for doing things concurrently, especially things that had to do with I/O, and networking I/O was especially a sort of a popular topic. And in the Python standard library, we had a brief period where there was lots of development, and I think it was late 90s, maybe early 2000s, and like two little modules were added that were the state of the art of doing asynchronous I/O, or sort of non-blocking I/O, which means that you can keep multiple network connections open and sort of service them all in parallel like a typical web server does.
So I/O is input and output. So you're writing either to the network or reading from a network connection, or reading and writing to a hard drive, to storage.
Also possible.
And you can do the idea is you could do it to multiple while also doing computation. So running some code that does some fancy stuff.
Yeah, like when you're writing a web server, when a request comes in, a user sort of needs to see a particular web page. You have to find that page maybe in the database and format it properly and send it back to the client. And there's a lot of waiting for the database, waiting for the network. And so you can handle hundreds or thousands or millions of requests concurrently on one machine. Anyway, ways of doing that in Python were kind of stagnated. And I forget, it might have been around 2012, 2014, when someone for the umpteenth time actually said, these async chat and async core modules that you have in the standard library are not quite enough to solve my particular problem. Can we add one tiny little feature? And everybody said, no, that stuff is not you're not supposed to use that stuff. Write your own using a third-party library. And then everybody started a debate about what the right third-party library was. And somehow I felt that there was actually a cue for, well, maybe we need a better state-of-the-art module in the standard library for multiplexing input-output from different sources. Mm-hmm. You could say that it spiraled out of control a little bit. It was, at the time, it was the largest Python enhancement proposal that was ever proposed.
And you were deeply involved with that.
At the time, I was very much involved with that. I was like the lead architect. I ended up talking to people who had already developed serious third-party libraries that did similar things and sort of taking ideas from them and getting their feedback on my design. And eventually we put it in the standard library. And after a few years, I got distracted. I think the big thing that distracted me was actually type annotations. Mm-hmm. But other people kept it alive and kicking, and it's been quite successful, actually, in the world of Python web clients.
So initially, what are some of the design challenges there in that debate for the PEP? And what are some things that got rejected? What are some things that got accepted that stand out to you?
There are a couple of different ways you can handle parallel I/O, and this happens sort of at an architectural level in operating systems as well. Like Windows prefers to do it one way and Unix prefers to do it the other way. You have an object that represents a network endpoint, say a connection with a web browser that's your client, and say you're waiting for an incoming request. Two fundamental approaches are, okay, I'm waiting for an incoming request. I'm doing something else. Come wake me up, or sort of come tell me when something interesting happened, like a packet came in on that network connection. And the other paradigm is, we're on a team of a whole bunch of people with maybe a little mind, and we can only manage one web connection at a time. So I'm just sitting looking at this web connection, and I'm just blocked until something comes in, and then I'm already waiting for it. I get the data, I process the data, and then I go back to the top and say, no, sort of, I'm waiting for the next packet. Mm-hmm. Those are about the two paradigms. One is a paradigm where there is sort of notionally a thread of control, whether it's an actual operating system thread or more an abstraction in async I/O, we call them tasks. But a task in async I/O or a thread in other contexts is devoted to one thing, and it has logic for all the stages. Like when it's a web request, like first wait for the first line of the web request, parse it, because then you know if it's a get or a post or a put or whatever, or an error. Then wait until you have a bunch of lines until there's a blank line, then parse that as headers, and then interpret that, and then wait for the rest of the data to come in if there is any more that you expect. That sort of standard web stuff. And the other thing is, and there's always endless debate about which approach is more efficient and which approach is more error prone, where I just have a whole bunch of stacks in front of me, and whenever a packet comes in, I sort of look at the number of the packet, that there's some number on the packet, and I say, oh, that packet goes on this pile, and then I can do a little bit, and then sort of that pile provides my context. Mm-hmm. And as soon as I'm done with the processing, I can forget everything about what's going on, because the next packet will come in from some random other client, and it's that pile or it's this pile. And every time a pile is maybe empty or full or whatever the criteria is, I can toss it away or use it for a new space. But several traditional third-party libraries for asynchronous I/O processing in Python chose the model of a callback. And that's the idea, where you have a bunch of different stacks of paper in front of you, and every time someone gives you a new sheet, you decide which stack it belongs to. And that leads to a certain style of spaghetti code that I find sort of aesthetically not pleasing, and I was sort of never very successful. And I had heard many stories about people who were also sort of complaining about that style of coding. It was very prevalent in JavaScript at the time, at least, because it was like how the JavaScript event loop basically works. And so I thought, well, the task-based model, where each task has a bunch of logic, we had mechanisms in the Python language that we could easily reuse for that. And I thought, I want to build a whole library for asynchronous networking I/O, and all the other things that may need to be done asynchronously, based on that paradigm. And so I just chose a paradigm and tried to see how far I could get with that. And it turns out that it's a pretty good paradigm.
So people enjoy that kind of paradigm programming for asynchronous I/O relative to callbacks. Okay, beautiful. So how does that all interplay with the infamous GIL, the global interpreter lock? Maybe can you say what the GIL is, and how does it dance beautifully with async I/O?
The global interpreter lock solves the problem that Python originally was not written with either asynchronous or parallelism in mind at all. There was no concurrency in the language. There was no parallelism. There were no threads. Only a small number of years into Python's initial development, all the new cool operating systems like SunOS and Silicon Graphics IRIX, and then eventually POSIX and Windows, all came with threading libraries that let you do multiple things in parallel. And there is a certain sort of principle, which is the operating system handles the threads for you. Mm-hmm. And the program can pretend that there are as many CPUs as there are threads in the program. And those CPUs work completely independently. Mm-hmm. And if you don't have enough CPUs, the operating system sort of simulates those extra CPUs. On the other hand, if you have enough CPUs, you can get a lot of work done by deploying those multiple CPUs. But Python wasn't written to do that. And so as libraries for multi-threading were added to C, But every operating system vendor was adding their own version of that. We thought, and maybe we were wrong, but at the time we thought, well, we quickly want to be able to support these multiple threads because they seemed at the time in the early 90s, when they were new, at least to me, they seemed a cool, interesting programming paradigm. And one of the things that Python, at least at the time, felt was nice about the language was that we could give a safe version of all kinds of cool new operating system toys to the Python programmer. Like I remember 1 or 2 years before threading, I had spent some time adding networking sockets to Python. And they were very literal translation of the networking sockets that were in the BSD operating system, so Unix BSD. But the nice thing was if you were using sockets from Python, then all the things you can do wrong with sockets in C would automatically give you a clear error message instead of just ending up with a malfunctioning hanging program. And so we thought, well, we'll do the same thing with threading. But we didn't really want to rewrite the interpreter to be thread safe, because that was like, that would be a very complex refactoring of all the interpreter code and all the runtime code, because all the objects were written with the assumption that there's only one thread. And so we said, okay, well, we'll take our losses, we'll provide something that looks like threads, and as long as you only have a single CPU on your computer, which most computers at the time did, it feels just like threads, because the whole idea of multiple threads in the OS was that even if your computer only had one CPU, you could still fire up as many threads as you wanted. Well, within reason, maybe 10 or 12, not 5,000. And so we thought we had conquered the abstraction of threads pretty well, because multi-core CPUs were not in most Python programmers' hands anyway. And then, of course, a couple of more iterations of Moore's law and computers getting faster. And at some point, the chip designers decided that they couldn't make the CPUs faster, but they could still make them smaller. And so they could put multiple CPUs on one chip. And suddenly there was all this pressure about do things in parallel. And that's where the solution we had in Python didn't work. And that's sort of the moment that the GIL became infamous. Because the GIL was the solution we used to sort of take this single interpreter and share it between all the different operating system threads that you could create. And so as long as the hardware physically only had one CPU, that was all fine. And then as hardware vendors were suddenly telling us all, oh, you got to parallelize. Everything's got to be parallelized. People started saying, but we can use multiple threads in Python. And then they discovered, but actually all threads run on a single core.
Yeah. I mean, is there ideas in the future to remove the global interpreter law, GIL? Like maybe multiple sub-interpreters, some tricky interpreters on top of interpreters kind of thing?
Yeah, there are a couple of possible futures there. The most likely future is that we'll get multiple sub-interpreters, which each run a completely independent Python program.
Nice.
But there's still some benefit of sort of faster communication between those programs.
But it's also managing for you this running of multiple Python programs. So it's hidden from you, right?
It's hidden from you, but you have to spend more time communicating between those programs, because the attractive thing about the multi-threaded model is that the threads can share objects. Mm-hmm. At the same time, that's also the downfall of the multi-threaded programming model, because when you do share objects, you didn't necessarily intend to share them, or there were aspects of those objects that were not reusable, you get all kinds of concurrency bugs. And so the reason I wrote that little blog post about semaphores was that concurrency bugs are just harder. It would be nice if Python had no global interpreter lock and it had so-called free threading, but it would also cause a lot more software bugs. The interesting thing is that there is still a possible future where we are actually going to, or where we could experiment at least with that, because there's a guy working for Facebook who has developed a fork of CPython that he called the no-GIL interpreter, where he removed the GIL and made a whole bunch of optimizations so that the single-threaded case doesn't run too much slower, and multi-threaded case will actually use all the cores that you have. And so that would be an interesting possibility if we would be willing as Python core developers to actually maintain that code indefinitely. Mm-hmm. And if we're willing to put up with the additional complexity of the interpreter and the additional sort of overhead for the single-threaded case. And I'm personally not convinced that there are enough people needing the speed of multiple threads with their Python programs that it's worth to sort of take that performance hit and that complexity hit. And I feel that the GIL actually is a pretty nice Goldilocks point between no threads and all threads all the time. But not everybody agrees on that. So that is definitely a possible future. The sub-interpreters look like a fairly safe bet for 3.12. So say a year from now.